The universe is a vast and mysterious place. We look up at the night sky and see countless stars. These twinkling points of light are not just beautiful, they are the building blocks of galaxies. Stars are giant balls of hot gas, mostly hydrogen and helium. They produce energy through nuclear fusion in their cores. This process releases tremendous amounts of light and heat. Stars come in many sizes and colors. Some stars are much larger than our sun, while others are smaller. The color of a star depends on its temperature. Hotter stars are blue, while cooler stars are red. Our sun, a yellow star, falls somewhere in between. Throughout human history, stars have captivated our imaginations. Ancient civilizations used stars for navigation and storytelling. Today we study stars to learn about the universe's origins and our place within it. The life cycle of a star is a fascinating journey. From their birth in stellar nurseries to their dramatic deaths, stars play a crucial role in shaping the universe we know. Stars are born in vast clouds of gas and dust. These clouds, known as nebulae, are scattered throughout galaxies. Nebulae are cold and dark, but they are also where stars take their first breath. Within these clouds, gravity acts as a sculptor, pulling gas and dust together. Imagine a cloud of flour in a baker's kitchen. If you gently blow on the flour, it will begin to clump together. Similarly, gravity gathers the material in a nebula, causing it to collapse in on itself. As more and more material clumps together, the cloud becomes denser. The center of the cloud heats up as particles collide. This is the beginning of a star's life. One famous example of a stellar nursery is the Orion Nebula. Visible to the naked eye, it appears as a fuzzy patch in the constellation Orion. Through a telescope, we can see the intricate details of this star-forming region. The Orion Nebula is a testament to the ongoing cycle of stellar birth and death. As the cloud collapses, it forms a hot, dense core called a protostar. This protostar is not yet a true star, it's still gathering material from the surrounding cloud. The protostar's core continues to heat up as it grows. The heat comes from the gravitational energy of the collapsing material. Think of a snowball rolling down a hill. As it rolls, it picks up more snow, growing larger and faster. Similarly, a protostar gathers more gas and dust, becoming hotter and brighter. The protostar is surrounded by a disk of material. This disk is where planets may eventually form. The Protostar Stage can last for millions of years. During this time, the protostar is not yet stable enough to produce energy through nuclear fusion. It's like a car engine trying to start, sputtering and flickering, but eventually, the protostar's core will reach a critical temperature. This is when the real action begins. When the protostar's core reaches a temperature of about 10 million degrees Celsius, nuclear fusion ignites. This is the moment a star is truly born. Nuclear fusion is the process where hydrogen atoms fuse together to form helium, releasing enormous amounts of energy. This energy creates outward pressure that balances the inward pull of gravity. Imagine a balloon being inflated. The air pressure inside the balloon pushes outward, preventing it from collapsing. Similarly, the energy released by nuclear fusion in a star's core creates outward pressure that counteracts gravity. This balance between gravity and pressure is what makes a star stable. Once a star achieves this balance, it enters the main sequence, the longest and most stable stage of a star's life. Our sun is currently a main sequence star. It has been shining brightly for about 4.6 billion years. Stars spend the majority of their lives in this stable phase. The length of time a star spends on the main sequence depends on its mass. More massive stars burn brighter and hotter, but they have shorter lifespans. Section 5, the Sun's Reign, a main sequence star. Our Sun, a yellow dwarf star, is a typical main sequence star. It's about halfway through its main sequence lifetime. The Sun's energy comes from the nuclear fusion happening in its core. Every second, millions of tons of hydrogen are converted into helium within the Sun's core. This process releases a tremendous amount of energy in the form of light and heat. This energy radiates outward from the Sun's core, eventually reaching the Sun's surface and then traveling through space to Earth. The Sun's energy sustains life on our planet. The Sun will continue to shine as a main sequence star for billions of years to come. However, like all stars, the Sun's fuel supply is finite. Eventually, the Sun will exhaust the hydrogen in its core. When this happens, the Sun will enter a new phase of its life cycle. Section 6. Giants in the Cosmos, the red giant phase. When a star like our Sun runs out of hydrogen in its core, it can no longer sustain nuclear fusion in the same way. The core begins to contract under its own gravity, causing it to heat up. This heat triggers the fusion of hydrogen in a shell around the core. The outer layers of the star expand significantly, causing it to become a red giant. Imagine a campfire. As the wood burns down to embers, the heat from the embers can still ignite dry twigs and leaves around the fire pit. Similarly, the hot core of a red giant star ignites fusion in the surrounding layers of hydrogen. During its red giant phase, the Sun will expand dramatically, engulfing the orbits of Mercury and Venus. Earth's fate is uncertain. It might be swallowed by the expanding Sun or pushed into a wider, more distant orbit. As a red giant, the Sun will be cooler than it is now, but much larger and brighter. Section 7. Stellar Relics, the fate of Sun-like stars. After spending millions of years as a red giant, a Sun-like star eventually sheds its outer layers into space. This creates a beautiful, expanding cloud of gas and dust called a planetary nebula. Planetary nebulae have nothing to do with planets. They got their name from their round, planet-like appearance through early telescopes. Imagine a dandelion after it has gone to seed. A puff of air sends the fluffy seeds adrift on the breeze. Similarly, a red giant star gently pushes its outer layers into space, forming a planetary nebula. At the center of the planetary nebula lies the star's exposed core, a white dwarf. A white dwarf is incredibly dense. A teaspoon of white dwarf material would weigh as much as an elephant. White dwarfs slowly cool down over billions of years, eventually fading away as black dwarfs. Section 8. When stars explode, supernovae. While stars like our Sun end their lives relatively peacefully, massive stars meet a much more dramatic fate. These stellar giants have much shorter lifespans than their smaller counterparts. When a massive star runs out of fuel, its core collapses rapidly under its own gravity. This collapse triggers a runaway nuclear reaction, resulting in a powerful explosion called a supernova. Imagine a building imploding, but instead of collapsing inward, it explodes outward with incredible force. A supernova is one of the most powerful events in the universe, briefly outshining entire galaxies. Supernovae are essential for life as we know it. The intense energy of a supernova creates heavy elements such as gold, silver, and uranium. These elements are scattered throughout the galaxy, enriching the interstellar medium from which new stars and planets form. Section 9. Cosmic Dancers, Neutron Stars. After a supernova, the core of the massive star is compressed to an extraordinary density, forming a neutron star. Neutron stars are incredibly small, typically only about 12 miles in diameter, but they pack the mass of two suns into that tiny space. A teaspoon of neutron star material would weigh billions of tons. Imagine taking all the cars in the world and crushing them into a single cube the size of a sugar cube. Neutron stars spin rapidly, emitting beams of radiation from their magnetic poles. If these beams sweep past Earth, we detect them as pulsars, objects that appear to blink on and off with incredible precision. Some neutron stars spin hundreds of times per second. Section 10. The universe's greatest mystery, black holes. If the core of a collapsing star is massive enough, not even the incredible density of a neutron star can withstand the crushing force of gravity. The core continues to collapse indefinitely, forming a black hole. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. Imagine a waterfall cascading over a precipice. The water plunges down, unable to climb back up. Similarly, anything that crosses a black hole's event horizon, the point of no return, is trapped forever. Black holes are still shrouded in mystery, but we know they play a critical role in the evolution of galaxies. Supermassive black holes, millions or even billions of times the mass of our Sun, lurk at the centers of most galaxies, including our own Milky Way. Section 11. From Death, New Life. The cycle continues. The life cycle of a star is a story of birth, life, death, and rebirth. The material ejected from dying stars, enriched with heavy elements forged in their cores and during supernovae, eventually becomes part of new stellar nurseries. Gravity once again draws this material together, collapsing clouds of gas and dust to form new protostars. Imagine a phoenix rising from the ashes. The death of a star is not an end, but a transformation. The elements that make up our bodies, the Earth, and everything around us were forged in the hearts of stars. The next time you gaze up at the night sky, remember that you are witnessing a cosmic dance of creation and destruction, a cycle that has been playing out for billions of years, and will continue for billions more. We are all stardust, connected to the universe through the life and death of stars.